When containers start to feel useful instead of just interesting, it usually happens when you stop thinking about the application alone and start thinking about its data. Applications are rarely valuable because they run for a few minutes, and they are valuable because they remember things, serve content, store records, or keep configuration that matters over time. That is where container storage becomes a real learning milestone, because beginners quickly discover that a container can be restarted, replaced, or deleted, and yet the system still needs the data to survive those lifecycle changes. The container model is intentionally disposable for the running instance, but the data model cannot be disposable unless you are doing a trivial demo. This episode builds your exam-level mental model for volumes and storage. What persistence means in containers, what mapping is doing at the boundary between host and container, what overlay concepts explain about where data actually lives, and why SELinux context awareness can decide whether something works or fails. If you can keep these concepts straight, container storage stops feeling mysterious and starts feeling like a set of predictable trade-offs. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A clean starting point is to define persistence in plain terms, because people often use the word as if it is a feature you either have or do not have. Persistence means data remains available after the process that created it is gone, and in container terms it usually means the data remains after the container instance is stopped and removed. That definition matters because it forces you to identify what event you are expecting to survive, such as a restart, a redeploy, or a complete replacement of a container. Beginners sometimes assume that because they can create a file inside a container, it must be persistent, but container file systems are often designed to be ephemeral at the instance layer. A container can write to its writable area while it is running, but that writable layer is tied to that specific instance and can be discarded when the instance is discarded. The whole point of persistence mechanisms is to separate durable data from disposable runtime state, so you can replace containers freely without losing the information that makes the service valuable. Once you adopt that separation as the goal, most storage decisions become easier to reason about. Mapping is the container storage concept that makes persistence possible in practice, and it is also the source of many beginner misunderstandings. Mapping is the act of connecting some storage that exists outside the container's ephemeral writable layer into the container's file system view. From the container's perspective, it looks like it is writing to a normal path inside its directory tree, but from the host's perspective, those writes are being redirected to a location that remains even if the container is removed. This boundary trick is powerful, but it also means you must care about both sides of the relationship, because permissions, ownership, and security controls are enforced on the host side even if the container believes it is in its own private world. Many container storage failures are not because the application is wrong, but because the mapping points to a host location that the container process cannot access safely. The exam-level takeaway is that mapping is not magic teleportation of files. It is a deliberate attachment of external storage into a container's path namespace. If you think of mapping as a controlled doorway, you will naturally start asking the right questions about what is on each side of that doorway. Volumes are one of the most common ways to implement persistence because they provide a container-friendly abstraction for storing data outside the container instance. Instead of treating the container's writable layer as the place where durable data should live, you treat volumes as the durable locations, and you mount those volumes into the container at paths where the application expects to read and write important data. A beginner-friendly way to understand this is to think of the container as a hotel room and the volume as a locked storage unit in the basement. You can change hotel rooms as often as you want, but your belongings are safe because they are in the storage unit, not in the room. Volumes also support reuse, meaning multiple containers can potentially access the same data if the design allows it, which can be useful for upgrades or migrations. The major point is that volumes are a durability and lifecycle tool, not just a convenience tool, and their main job is to break the tight coupling between the container instance and the data it uses. Once you see volumes as lifecycle control, their importance becomes obvious. There is also a related concept that often gets mixed up with volumes, which is the idea of mounting a host directory directly into the container. In many container discussions, you will hear people talk about bind mounts, which are essentially direct mappings from a specific host path into a specific container path. You do not need to become tool-specific to understand the concept, because the mental model is the same as mapping, but the implications are different. A direct host mapping can be very flexible because you know exactly where the data is on the host, and you can inspect it with normal host tools. The trade-off is that you have to manage permissions, ownership, and security labeling carefully because you are exposing a real host directory into the container. That exposure can be useful for development workflows, but it can also increase risk if sensitive host locations are accidentally mapped into a container. At exam level, the key point is that direct host mapping can make persistence straightforward, but it also makes the boundary between host and container more visible and therefore more sensitive. If you treat direct mapping as a powerful but sharp tool, you will make safer decisions. Overlay concepts are the next piece that turns container storage from a vague idea into something you can actually picture. Containers commonly use a layered file system approach where the image provides read-only layers, and the running container adds a writable layer on top that captures changes made at runtime. When the application writes a file that did not exist, that file lands in the writable layer. When it modifies a file that came from the image, it can create a copy in the writable layer that shadows the original, which is why you can change apparent content without changing the image itself. This layered approach is efficient, but it is also the reason beginners get confused about where data lives, because the container view is a merged view of multiple layers. The overlay idea explains why a container can appear to have a full file system while still being mostly read-only image content plus a thin layer of runtime changes. It also explains why deleting the container can delete those runtime changes, because the writable layer is tied to the container instance. If you keep overlay in mind, you stop asking where the file is in the container and start asking which layer it belongs to. Once you understand overlay behavior, the logic of persistence becomes almost unavoidable. Data that lives only in the container's writable layer is not designed to outlive the container instance, so anything valuable should be moved out of that layer and into a persistent mapping like a volume. This is not just about avoiding data loss, but about making container behavior predictable across redeployments. If you rebuild an image and run a fresh container, you want the application to start cleanly while still finding the same durable data where it expects it. Beginners sometimes try to treat the container as a long-lived machine and keep accumulating changes inside it, but that approach fights the container model and leads to unreproducible environments. The exam-level reasoning you want is that containers are meant to be recreated from images, and persistence mechanisms are how you keep state while allowing that recreation to happen safely. When you hear a scenario where changes disappear after a redeploy, overlay and the ephemeral writable layer are the first concepts you should recall. That is not a trick, it is a direct consequence of how layered file systems work. Storage mapping also introduces a category of failures that look like application bugs, but are actually access control mismatches. A containerized process may run with a particular user identity inside the container, but the host file system enforces permissions based on host identities and policy. If the map directory is owned by a different user or has restrictive permissions, the application might fail to start or might run but fail to write data, which can look like a mysterious crash or a silent failure. Even more confusing, the container might be able to read but not write, which can cause partial functionality that is hard to diagnose by symptoms alone. This is why container storage is not only a data topic but also a security topic, because access control determines whether persistence is safe and whether it works. A beginner should learn to treat storage problems as boundary problems, where the container process is crossing into host-managed territory through a mapping. When you adopt that perspective, permissions issues stop being random and start being the expected place to look when persistence behaves strangely. Context awareness becomes even more important when the host is enforcing mandatory access control (MAC) policies, because those policies can block access even when traditional permissions appear correct. Security-enhanced Linux (SELinux) is a major example. and it changes the container storage story because it introduces an additional labeling system that controls what processes can access which files. The key concept is that files and processes can have security contexts, and the policy can allow or deny access based on those contexts. In a container scenario, you can have a mapped host directory that looks writable based on ownership and permissions, yet access is still denied because the labeling does not match what the container process is allowed to touch. Beginners often misinterpret this as the container engine being broken or the file system being corrupted, when the truth is that the security policy is doing exactly what it was designed to do. At exam level, you do not need to author policies, but you do need to recognize that SELinux can be the deciding factor when a container cannot read or write mapped storage. If you remember that SELinux is an additional enforcement layer, you will not get trapped by the illusion that permissions are the only access control mechanism. The most practical mindset for SELinux in container storage is to treat it as part of the host's contract, not part of the container's imagination. Containers might feel isolated, but they are still processes on the host, and the host security model still applies, especially when those processes touch host resources like mapped directories. When you map storage, you are effectively asking the host to allow a containerized process to interact with host files, and SELinux may require that those files carry labels that match the intended use. This is where context awareness becomes a troubleshooting skill, because the symptom might be a storage failure, but the cause is a policy mismatch. A beginner-friendly way to think of it is that SELinux adds a second lock to the door, and your key must fit both locks for access to work. If you only check the first lock, which is Unix permissions, you might believe everything is correct while the second lock is still refusing entry. The exam often rewards the learner who remembers that security policy can block operations that would otherwise be allowed. Container storage also intersects with system stability and performance in ways that are worth understanding at a conceptual level. Overlay-based writable layers can be efficient for transient writes, but they are not always ideal for heavy, durable workloads, especially when the data must persist and be reliable across container replacements. Using a persistent mapping can make behavior clearer and can simplify backups, because the data lives in a known location outside the ephemeral container layer. At the same time, mapping large host directories or sensitive paths can create risk if the container is compromised, because the attacker's process may gain access to data that should have been isolated. This is why storage decisions are inseparable from security decisions, even in beginner contexts. The right mental habit is to map only what is necessary, keep the mapped scope narrow, and treat persistent data as a controlled interface rather than a convenient dumping ground. When you hear questions about least privilege in container environments, storage mapping is one of the places where that principle is applied. A container that only sees the data it needs is safer than a container that can browse the host file system. Another important beginner misunderstanding is assuming that persistence automatically means safety, as if storing data outside the container instance makes it secure. Persistent data still needs protection because it can contain secrets, credentials, logs, or business records, and mapping it into containers creates additional access paths. If multiple containers can access the same data, you must think about whether those containers should share that access or whether isolation is required. You also need to consider that the host administrators can access the mapped data directly, which is often desirable for recovery, but it also changes the trust model compared to data locked inside a container instance. For Linux plus reasoning, it is enough to connect persistence with lifecycle and to connect security with access control and scope. A persistent volume can make services resilient, but it can also become a high-value target if it stores important information. This is another place where SELinux and other access controls matter, because they can reduce the blast radius of a compromise by limiting what the containerized process can touch. Thinking about persistence and security together is exactly the kind of integrated understanding the exam wants to see. The overlay concept also helps you interpret what it means to upgrade or roll back a containerized application, which is a common operational story even at a high level. If the application is updated by building a new image, the new image layers replace the old image layers for new containers, but the persistent data stays the same if it is mapped appropriately. That means you can roll forward or roll back application versions by choosing different images, while the data remains consistent across those changes. Beginners sometimes fear upgrades because they picture the entire environment being rebuilt, but containers are designed to separate the application file system from the durable data. That separation is why you can replace a container without losing its database files or content store, assuming the mapping is correct. It also means that if the data schema changes, you must be cautious, because persistence preserves data even when the application changes, which can create compatibility issues. At exam level, the main idea is that container images are replaceable, and persistence mechanisms are what allow replacement without data loss. When you can articulate that, you can reason clearly about container lifecycle questions. A strong troubleshooting mindset for container storage begins with deciding whether you are dealing with ephemeral state or persistent state. If a change disappears when a container is replaced, suspect that the change lived in the container's writable layer rather than in mapped storage. If an application cannot write to its data directory, suspect a boundary access issue, which can include basic permissions, ownership mismatches, or SELinux labeling problems. If data appears in an unexpected location on the host, suspect that the mapping points somewhere different than you intended, which can happen when paths are misinterpreted or when defaults are applied. If two containers see different data, suspect that they are not sharing the same persistent mapping, or that one is using its ephemeral layer by accident. This style of reasoning is not about memorizing a checklist, and it is about asking the right class of question first, so you do not waste time chasing the wrong layer. The exam often uses these scenarios because they test whether you understand the architecture rather than whether you can remember a specific command. A learner who can place a problem into the right layer is already doing most of the work. To bring everything together, volumes and storage in containers are about controlling where state lives so that container instances can remain disposable while data remains durable. Persistence means the data survives beyond the life of a container instance, and mapping is the mechanism that connects durable host-managed storage into a container's file system view. Overlay concepts explain why container file systems look complete while actually being a stack of read-only image layers plus a container-specific writable layer that is usually ephemeral. That layered design is efficient and flexible, but it can mislead beginners into thinking their changes are permanent when they are not. SELinux context awareness matters because it adds policy enforcement that can block container access to mapped storage even when traditional permissions look correct, and recognizing that can save a lot of confusion. The most exam-ready mindset is to think in boundaries, layers, and intent. What should persist, where it should live, and what access controls must allow it. When you can explain those relationships clearly, container storage becomes a predictable part of Linux system behavior rather than a collection of surprising exceptions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.